Hello everyone, my name is Yilun Chen. Today I will present our paper, Understanding Memory and Thread Safety Practices and Issues in Real-World Rust Programs. This is a joint work across Penn State University, Purdue University, and UC San Diego. Rust is a young and popular programming language for building low-level software, such as OSs, distributed systems, and web browsers. Rust is designed to provide both efficiency and safety by inheriting most C and C++ features by enforcing strict compile time checks. Rust's safety mechanisms are centered around the concepts of ownership and lifetime. Each value has one and only one owner variable. A value is dropped and cannot be used anymore when its owner variable's lifetime ends. Rust allows programmers to borrow a value's ownership using reference. As in this example, Y borrows the ownership of value Z. A reference can be immutable or mutable. Rust allows multiple immutable references, but at most one mutable reference at any time. As in this example, X and Y cannot be both mutable. Essentially, Rust prohibits both aliasing and mutability at the same time. With Rust safety mechanisms, many memory and concurrency bugs can be prevented at compile time. However, safe code alone is not enough to build real system software. With just safe code, programmers cannot reuse external libraries or access low-level resources such as OS and hardware interfaces. In addition, safety checks can sacrifice some performance. To mitigate the limitation of safe code, Rust allows programmers to use unsafe tags to bypass certain safety checks. A function can be marked as unsafe. A piece of code inside a function can also be marked as unsafe. For the latter, the function can still be called in safe code. We call this pattern interior unsafe. Rust's safety rules are very different from traditional languages, and it gets even more complicated when unsafe code is introduced. Although Rust has been adopted by more and more developers in recent years, there are many key questions that remain to be answered. For example, how well can programmers grasp Rust's complex safety rules? Can safe code in Rust still have issues? How does unsafe code impact the correctness of Rust software? And how can they be properly written? We believe that the best way to answer these questions is through understanding of real-world Rust software. Thus, we conducted the first empirical study on Rust safety practices and issues. Our study covers three aspects: how unsafe code is used, removed, and encapsulated in real-world Rust software, what type of memory bugs and what types of concurrency bugs are there in real-world Rust software, and how are they fixed. To conduct our study, we selected a set of large, mature, and open-source Rust software, including 5 popular Rust software systems, 5 popular Rust libraries, the Rust standard library, and 2 online vulnerability databases. We collected memory and concurrency bugs from this open-source software by searching GitHub commit logs with relevant keywords. We also included all the bugs in the 2 vulnerability databases. We then performed manual, close inspection of all our collected usage cases and bugs. We examined hundreds of unsafe code usages, memory safety issues, and thread safety issues. With our detailed analysis of them, we made 11 insights and 8 suggestions which can help Rust programmers and the future development of Rust language. To demonstrate the value of our study, we also built 2 bug detectors which found 10 previously unknown bugs. In the rest of my talk, I will go over different parts of our study in different levels of details. Now let's first look at how unsafe code is used in the real world. Our study of unsafe code usages answers 3 questions. Why do developers use unsafe code? How is unsafe code removed? And how is unsafe code encapsulated? Due to the time limit, I will only cover the first question. Please refer to our paper for the second and third questions. To understand why developers use unsafe code, we analyzed 450 randomly sampled unsafe code usage cases. We found that the most common reason is to reuse external libraries like glibc. The second most common reason is to improve performance. Other common reasons include sharing data across threads, like accessing a global variable, and various ways of bypassing different compiler checks. One surprising finding is that for 5% of unsafe code usages, the unsafe keyword can be removed without resulting in any compilation errors. After digging into these cases and communicating with the original developers, we found that the code is marked as unsafe for good reasons. If you are interested in finding more about it, please read our paper. Overall, we found that most unsafe usages are for good and unavoidable reasons. Now, the question is, if unsafe code is unavoidable, how can we avoid or minimize the issues of unsafe code? To answer this question, we need to have a good understanding of real-world bugs. Let's look at our findings in memory safety issues. We collected and inspected 70 memory bugs, including all reported bugs from CVE and RustSec databases. Our analyses are along 3 dimensions. How do errors propagate? What are the effects of those memory bugs? And how are bugs patched? Due to the time limit, I will only cover the first 2 in this talk. To understand how safe and unsafe interact for memory bugs, we analyze the error propagation chain from a memory bug's cause to its effect, and consider how safety semantics change during the propagation chain. We consider the code where a bug's patch is applied as its cause, and the code where the error symptom can be observed as its effect. Let me use a use-after-free bug example to explain the error propagation chain. The match code block checks whether or not the input data is none. If data is not none, a bear object is created and pointer P points to that object. The lifetime of buy object terminates at the end of the match block, and it is freed there. Thus, pointer P becomes a dangling pointer after the match block. Later on, when P is dereferenced inside this function, use-after-free happens. The root cause of the bug is that the buy object is automatically dropped earlier in a piece of safe code. The effect happens later when P is dereferenced inside unsafe code. Therefore, the error propagation chain for this bug is from safe to unsafe. Based on this taxonomy, we have 4 categories of memory bugs: safe to safe, unsafe to unsafe, safe to unsafe, and unsafe to safe. There's only one bug whose cause and effect are both in safe code. The bug only happened in a very old Rust version. All the other bugs involve unsafe code in their error propagation chain. Surprisingly, many memory bugs also involve safe code. Thus, future memory detection tools cannot just focus on unsafe code. They should also inspect the related safe code. Now that we understand how errors propagate, let's look at what effects our studied memory bugs have. We categorized them into raw memory accesses and lifetime violations. Raw memory accesses include buffer overflow, non-pointer dereference, and read uninitialized memory. These bugs are caused by traditional reasons, and it is promising to apply traditional bug detection tools on them. Lifetime violations include invalid-free, use-after-free, and double-free. These bugs are caused by the misunderstanding of Rust lifetime rules. Since they are unique to Rust, we believe that new bug detectors are needed for Rust. Other than advice for bug detectors, we also make some suggestions to programmers on how to avoid memory bugs. Since all memory bugs involve unsafe code, we should properly encapsulate them by performing careful checks. When entering unsafe code, programmers can check the preconditions such as the validity of the pointer input to the unsafe code. When leaving the unsafe code, programmers can check the post conditions like the correctness of the return value to guarantee the correctness of the subsequent code. I've just covered our findings and suggestions of memory bugs. Now let's move to thread safety issues. We studied both blocking bugs and non-blocking bugs for thread safety issues. Blocking bugs happen when one or more threads are unintentionally stuck in their execution. A typical type of blocking bug is deadlock. Non-blocking bugs happen when all threads can finish their execution, but with undesigned results, such as data race. For blocking bugs, we study which operations cause a thread to be blocked and how they are fixed. For non-blocking bugs, we study how threads communicate with each other and how they are fixed. I will only be able to cover some of our results of blocking bugs. Please read our paper for the rest. Similar to other programming languages, blocking bugs in Rust software are mainly caused by the misuses of synchronization primitives like logs, conditional variables, and channel, with the misuses of log being the most common case. One interesting finding we have is that among these misuses of logs, many are caused by the misunderstanding of Rust lifetime rules, and they show exactly the same pattern. Rust locking mechanism is designed to protect the data instead of code regions. To safely share a variable across threads in Rust, the variable must be declared with both arg and mutex. Arg tracks the lifetime of a variable and provides read-only accesses to threads. Mutex provides write access. In this example, when mutex lock is called, a reference of the protected variable is returned and it can be used to access a variable. When the lifetime of the reference ends, unlock is automatically called by the Rust compiler, so Rust lifetime rules determine when unlock is called. Now let's look at a double lock bug from TIKV, which is caused by the misunderstanding of Rust lifetime rules. The variable client is an object of inner that is protected by a mutex. Client's lock is then acquired, and the inner object is used as the input of function connect. The match block checks the return value of connect. If OK is returned, the lock is acquired again to modify the inner object to MBRS. However, the first lock is not released until the end of the match block. Thus, when connect returns OK, we will have a double lock. The fix of this bug is to save the return value of function connect to a local variable, and then use a local variable as a condition of the match block. Since the first lock is immediately dropped after calling connect, the double lock is avoided. There are many other bugs exactly like this one. We found that the misunderstanding of Rust lifetime rules is a common cause for blocking bugs. We suggest a future IDE to highlight the location of implicit lock. Here is a screenshot of an IDE plugin we developed after this project. It highlights the lock scope for the first lock of the previous double lock bug, so that developers can easily notice the error. We also suggest Rust to add explicit unlock APIs to give programmers more control over the lock scope. Now, I have briefly walked through our study, and here are some of our final thoughts. Rust started with a very elegant design that is both safe and efficient. However, when used in reality, it gets less elegant because programmers have to also use unsafe code, and it can lead to many new issues. To review these issues, we performed the first empirical study on Rust safety usages and issues and learned a set of lessons from the real world. The most important lesson is that when real usages goes beyond the original language design philosophy, we need to build new tools for this extra part. Finally, we hope that our study could also give some hints and warnings to other languages and future language designers that it is important to look at real-world usages and issues. Thank you. I will open the floor for questions. Also, a reminder that all of our study results are available at this link.